today I wanted to start by trying to describe the intensity of the double slit, go away from kind of the idealized case that we've been looking at, and then hopefully I also have time to describe the thin film interference. So that's my plan for today. So questions, comments, concerns about where we are, where we've been, where we're heading? Then in my very, very idealized world, this value L much greater than D, even though I'm not drawing it that way just because, again, limited board space, not a good artist, and somewhat lazy. To my best efforts, at least, R1, R2. Then, if we wanted to describe intensity, well, at some point P located some height y off of the central axis, welcome. Then one way of thinking about this is to begin by talking about the electric field. And so remembering that light is an electromagnetic wave, we could focus on one piece or the other, E or B. I'm going to focus on E just because it's, I guess, what's more commonly done. And so what I would argue then is that E1 could look like E naught times sine of omega t. Yay? And assuming that monochromatic coherent light source instant at the two slits, then E2 should have the same frequency. It should just be phase shifted by some amount B corresponding to the extra travel of ray 2 compared to ray 1. Does that make sense? And so then we could write E2 would then just look like E naught sine omega t plus phi. Is that sort of all right? We could describe the extra travel length, delta, delta R, however you want to call this, R2 minus R1. This looks just like it did last Wednesday, where we said that this was equivalent to d sine theta. So
that R2 minus R1 minus d sine theta?
Oh, that's an equals. Sorry. Thank you. So far, so good? We could sort out what we mean by this in terms of, we could sort out what delta R means in terms of phi. We could describe this as delta R or delta over lambda, right? So this is like one of those analogy questions that I guess people don't have to take the SAT or the ACT anymore.
I do.
I did.
Really?
Yeah. I gotta take the ACT.
They're fun. I love stuff like that. So,
You don't like English.
oh, I'm not talking about the graduate record exam portion. I'm talking about I'm talking. When I was young, we had to take like a exam at the end of high school.
Yeah.
So, my brothers and I scored percentile identically, but they renormalized the exam between when my brothers took it and when I took it. They renormalized upwards to make a 1,000 average, I think, to make people feel better. And so my score is numerically higher than my brother's, even though the percentile is identical. But, you know, as far as I'm concerned, it's the score that counts. So
How much percentile? 60, 90?
99.
Wow.
I was a National Merit Scholar, so
You're a genius.
no,
99%.
there's a long ways between me and a genius, I promise.
Oh my God.
I scored perfectly on the PSAT. I did not score perfectly on the SAT. I came close. I like standardized tests, which, again, congratulations, you guys get to take a test on Wednesday. It's not standardized, I'm sorry.
Okay, shut up.
Um,
Sorry, I didn't have a good sleep. I don't mean that.
So, this is like one of those analogy questions on the SAT or the ACT. This is to this as what is to what. So, delta or delta R, right, is to a wavelength as phi is to what? So delta R is a fraction of a wavelength, right? So delta R is to lambda as phi is to
Delta R.
in terms of angle. So I want phi to be an angle. So lambda represents what? A whole wavelength. And so what corresponds to one full cycle for a wave?
2 pi?
2 pi. So 2 pi radian.
No.
Hooray? And so we can then say that phi is going to be 2 pi times delta over lambda. If I rewrite that slightly, we get something in that family. Yay? But we already said delta was d sine theta. And so we could rewrite this as 2 pi over lambda times d sine theta. Yes, no, maybe so?
So in here, the wavelength is the wavelength of the
Of the monochromatic coherent light source. Hooray? The stuff that we're making interfere when it gets to here. All right, then. Well, what do we think that E at P should be?
Should be epsilon 0 sine.
Can I just say E1 plus E2
Okay.
for now? No one's too cranky about that. Wonderful. So we could write this, I think, as Susan was trying to lead us, as sine omega t plus sine of omega t plus b in quantity times E naught. Yay? Then I'm going to do that thing that I always hate when teachers do, because to be honest, I didn't actually recall this, right? I'm going to say recall. And I'm going to read this from my notes. That sine of A plus sine of B. Just out of curiosity, does anyone know what sine of A plus sine of B is?
1.
Sine squared of A plus cosine squared of A would be 1. This one winds up being 2 sine A plus B over 2 times, oh, drops, I ran out of space. It's trying to be all fancy. So 2 sine A plus B over 2 times cosine A minus B over 2. And so here, I'm going to suggest that we let A equal omega t plus phi, and B equal omega t. And so what kind of cool thing happens then? So E naught, I guess I need to multiply by 2. Times, well, what is A minus B? B. So cosine of B over 2 times sine of what?
Omega t plus 5 divided by 2.
True story. Yay. This is somewhat interesting, right? The electric field intensity varies as with the same frequency as that of the source, right? Interesting, maybe not surprising. Guess it kind of depends on what you were expecting here, but for me, interesting. A little surprising. So the amplitude, so how does the amplitude compare to say, the amplitude of just, say, one of these things?
So twice.
So it's got the same frequency. Omega. The amplitude goes from E naught to, so from 1 E naught to 2 cosine of B over 2 times E naught. Right, so it goes from 1 to 2 cosine B over 2. Or the amplitude is multiplied by 2 cosine B over 2. So I'll ask, what happens at, say, B is equal to 0, 2 pi radian, 4 pi radian, 6 pi radian, so on and so forth?
2 equals 0. No, 2 E naught. Just equal.
Just get to,
0, cosine 0 is 1, right? So 2 times E naught.
Either 2 times 1 or 2 times minus 1, right?
Oh, yeah, minus 1, yes.
Yay?
Yes.
What happens when B is equal to, say, pi or 3 pi or 5 pi?
0.
Now you get 0. Yeah?
Yes.
And so for small angles, meaning that y is small compared to L, right? Then sine of theta is roughly equal to y over L. Right? Sine theta is approximately tan theta is approximately y over L
for small angles.
for small angles. Yay?
Yeah.
So then I will tell you how things really detect light. So almost all light sensors aren't looking at, so if we put a light detector, symbol I use for that is a badly drawn human eye. Grad students, undergrads, cheap labor, right? Price of silicon semiconductors is coming way, way down, right? Price of a Milky Way candy bar, I'll stare at light for you all day. So most light measurements, well, light measurements in general, intensity doesn't go as E, it goes as EP squared. So the intensity at point P goes as EP squared. And most, so I guess we could say that, what is that going to look like? It's at least proportional to 4 E naught squared cosine squared B over 2 times sine squared of omega t plus V over 2. Most light detectors, like the eye, are actually time averaging. They're looking at the time averaged intensity. And so So here's where something nice happens to us. What is the time average of sine squared over a full cycle?
Can you repeat the question again?
what is the time average of sine squared over a full cycle? So what's the biggest it could be?
1.
1.
What's the smallest sine can be, not sine squared?
Small is -1.
Okay. So the smallest it could be is -1. The biggest it could be is 1. So if we're talking about sine squared, then the smallest it could be is
0.
0. And the biggest it could be is
1.
1. And so if you had to guess because you didn't know, what's the average value of sine squared over a full cycle?
0.5.
Half, right? So over integer number of cycles, I suppose, is a better way of saying this. And so we can say that the intensity goes as this maximum intensity times cosine squared of b over 2. But long ago, probably with my dull droning monotone feels like ages ago, we were talking about ratios or analogies and the SAT, the ACT. We already had a statement of what we meant by phi. And so we could write this as,
Why this is hard?
Because the highest it can be is 1, and the lowest it can be is 0. So, if it,
1 minus 0 is 1, right? Why half?
this is the average, so this is the value of it, the average value of it over a cycle.
you can also prove it to yourself if you enjoy integration by parts.
Oh,
Um,
I believe you.
that's the threat of every physics teacher. Is, you know, just say, well, you can show it to yourself if you want to spend some time with integration by parts.
Like 1 plus 0 over 2.
Yeah.
We're happy enough with this. Okay, so since we also have that for small angles, sine of theta looks like y over L, we can say that for small angles, I looks like I max times cosine squared of pi d y over lambda L. Modulo order, it looks the same as my notes, which makes me feel better. Note that this implies that as you scanned back and forth, right, that you're going to get variations in intensity. And so while this is, please note that I knew I wasn't going to be able to draw this before I tried. Opening myself up to ridicule here.
What
Because
is
I care.
I max in the last equation?
Note that I told you here that the intensity is proportional to this, right? It's not exactly for E naught squared cosine squared b over 2 times this varying piece. And so I just buried in this the constant of proportionality. So this is proportional to Imax. This times something else is Imax. Just not going to go into that because, again, that's a physics 230 concept, not a physics 231 concept.
Do we have to worry about calculating the Amax, or it's just for derivation purposes?
No, if I asked you to do something in this fashion, I would give you what Imax was.
Okay.
But that's possibility of that happening is very low. Very, 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 very low. Okay, so this is kind of our double slit pattern, right? And note that, somewhat even spacing to the best of my ability to draw, and all has the same amplitude, yeah?
Yeah.
If I tried to map onto this, this type of statement, well, what happens when y is 0? What do I get?
Imax.
I get
Imax.
Imax, right? So,
Now I have
oops, and actually I shouldn't do it like that because that's going to obscure what I wanted you to see. You know what? Let me do this on a separate. So, note that if I can make y look like, where does cosine go to 0?
pi over 2.
Pi over 2. So what does y need to look like to get to my first 0?
1, 0.5.
Well, so I need y times pi d divided by lambda over L to equal, or sorry, I need y times d over lambda L to equal half, right?
Yeah.
So this is for a minimum, the first minimum in fact. And so we can say y min 1 is equal to lambda L over 2D. Did I get that right? Yay? So if I plug that in for this y, I wind up with the stuff in this argument, right? Goes to pi over 2 radian. Cosine of pi over 2 radian is 0. Cosine squared of pi over 2 radian is also 0. And so, let's see. So, do you guys agree that if I was plotting intensity, that it does something like that? Maybe more symmetric than that, but bear in mind I'm an old man. Yay? Do you see that we could get to another maximum, so maybe this does something like this, right? And it keeps dropping off like so. Yeah? Does that work or no? Then if I map this on top of this, what I wind up getting is maybe something like this, right? should be more symmetric than I'm drawing this, but again, thought that counts. What I get are kind of an enveloping effect. We grew up in different eras.
Yeah.
You didn't have to agree that readily. Little self-conscious. My hair is graying. Seen dinosaurs with fewer wrinkles.
So,
Quite literally, I've seen dinosaurs, which speaks to how old I am. But
That is a requirement.
But when I was young, the cool thing to do, it wasn't cool, but playing around with radios was like building your own radio. It didn't get much cooler than that. So, anyone ever, what are the two main bands of radio that we use?
AM, FM,
AM, FM. What does FM stand for?
frequency modulation,
Frequency modulation. What does AM stand for?
amplitude modulation.
Amplitude modulation. So, which bands are the numbers on the dial spaced further apart?
I think it's right, 88 megahertz.
FM is spaced much further apart, right? So I don't know what cool radio stations are, but you could have are there cool radio stations anymore? Is it just for dinosaurs?
98.1.
Okay, I'll take your word for it.
I would look at Fox News.
So these are spaced by 0.2 megahertz. What's a megahertz again?
Megahertz. Oh, mega is
1,000 kilohertz.
how many?
Million, 1,000 kilo. So this is spaced by 200,000 hertz, yeah? Yes, no, maybe so? So the spacing, yay? I think we talked about this quite recently. In the event that my beloved San Francisco Giants ever get to play a game this year, you will find them and love them on 680, KNBR 680. But that's on the kilohertz band. And so what's the next allowed step? There isn't anything on the next allowed step. Right? 690 kilohertz would be the next allowed step. What is the step size for AM?
10 kilo.
Is spacing of 10 kilohertz. Let's see if we can sort out why this is true. You guys told me that, what are we messing with in FM?
Frequency.
We're encoding the signal that we want to transmit by varying the frequency. If you space those close together, what's going to happen?
You cannot hear.
You're going to bleed across into your neighbor, right? And so if that happens, neither of your signals make it to anyone. The FM, the stations need to be spaced far enough away that you can vary your frequency without running across your neighbor's property, right? Does that make sense? Amplitude modulation, you are stuck on your frequency and you can't vary from that, otherwise you're going to get in trouble. Because you'll ruin anyone's ability to hear your or your neighbor's signal. So what are you doing there? Well, in amplitude modulation, it is what it sounds like. You are restricted to staying on your frequency. But how are you going to send out information? Well, what you're going to do is you're going to envelope this. You're going to carry the information that you want to transmit in the amplitude of the wave. And so you might So you aren't going to change your frequency. What you are going to do is you're going to change the amplitude. And so someone wanting to get whatever signal you're sending, the information is buried in the amplitude of the signal, and kind of the rate of change of the amplitude of the signal. That's what we're doing here. We have our carrier signal, right? This is like our 680 kilohertz. It is going to be amplitude modulated by this term out front, right? By this guy. And so the amplitude at various values is going to be meted out by what this tells us, right? So this sets the envelope for this, much like this dashed line sets the envelope for this. Does that make sense?
I'm a bit confused. The top one represents.
This is just an ideal double slit interference.
This guy right here, right?
The ideal, right, where we don't have to worry at all about any kind of diffraction interference effect.
And the bottom one?
This is what we were just doing, where we are starting to worry about modulation, right? We are that is far down the line. Let me go slightly out of order here and give you an explanation for where wow, that is way down the line. It's not slightly out of order. All right. We will do this way out of order. Although, all right. So let's imagine that we had a single slit.
Oh my God.
The double slit is made of two slits, right? But let's just imagine we had a single slit. That's intended to be my center line. Symmetric. You. Okay. wanted to divvy this up into pieces, right? So here's the slit, but I wanted to divvy this up into segments so that we have an ability to compare rays traveling through different parts of the slit. And so trying to draw these all parallelish. I'm going to label these 1, 2, 3, 4, and 5. So the width of this slit is A, and in a similar fashion to what we did when we were looking at double slit interference, will you guys stipulate that that is close enough to a perpendicular drop line?
Yes.
Yeah.
Okay, thank you. Then, what is this extra path length that 1 travels compared to 2?
So, sine
Whatever.
of theta times A over 4.
So that's, that one's A over 2, that one's A over 4, right? So we're happy-ish with this? So let's do this in a way that, let's use the A over 2 instead of the A over 4, just to, yay? Then, do you agree that there is an added path length for 1 compared to 3? That is just A over 2 sine theta? And so we could also say that 2 and 4 have that same thing going on. Yeah? That basically pairwise I can always find a partner to match this. And so upper half of slit rays.
Couldn't we also say 5 and 3?
Sure. I just want to say pairwise I can find any one in the lower half that will partner with one in the upper half. They differ by A over 2 sine theta. So when will rays in the upper half interfere destructively with rays in the lower half.
When a over 2 sine theta is equal to lambda over 2.
Yep. Okay. Or that